Okay. So I will be auditing the Carnegie Mellon course on Introduction to Computer Systems, mainly because I want to read this book. It was came highly recommended and has sections on virtual memory that I think I could do with reviewing. And yeah, seems to have a lot of good exercises. They mentioned writing a shell, which is something that I wanted to do as an exercise for a while now. Implementing malloc, which I did at the end of KNRC. Not on my own, of course. I leveraged heavily the example that they provided. But it does work. It does malloc stuff. I've been feeling really drained today, for sure. I think tomorrow I'm gonna take it easy. I took it easy kind of today. I didn't get a lot of hours in studying, but tomorrow I'm just gonna I'm gonna take it as a rest day. I tried to push it today, and my brain and body are just like, no, you're not pushing it. So yeah, I took a nap this afternoon, really long nap, and tomorrow I think I'm gonna take some time off as well. Okay, this repo tracks my progress on should have deleted that. Oopsie. Let's watch the first lecture, why not? I fixed the latency issue with my HDMI audio. It was OBS monitor got messed up somehow. So I just disabled monitoring in OBS, and when I re-enabled it, everything works fine. So let's go ahead and watch this first lecture here. And I wonder if I can watch it in 2x speed. That'd be nice. Let's see here. Speed. 2x. Bam.
Hello, everyone. I'd like to welcome you all to this this term's instance of this course is officially either 15213 from computer science or 18213 from electrical and computer engineering. But a large number of the people enrolled in this course are in one called 513, which is for graduate students. And to be totally honest, you're not supposed to be here because you're supposed to watch the videos, the lectures by video later. But we're not checking any cards, so I don't really know who you are. Anyways, this course is, as you can see, a very popular course on campus. We have over 600, shouldn't exaggerate, students on campus enrolled in one of those three versions of the course, which if you think about a university of the size of CMU, that's like about 5% of the total student population. So we're very glad to have you here. You overdid the game. Try that, that's better. So my name is Randy Bryant, and my co-instructor is Dave O'Halloran, and those names might be familiar if you have been to the bookstore, because the book was written by us. And we actually wrote this book. We started 213 as a course in 1998. And I know that you're told.
Why did this guy reverse into the room?
Dave O'Halloran, and those names might be familiar if you've been to the bookstore, because the book was written by us. And we actually wrote this book. We started 213 as a course in 1998. And I know that you were children then and all that stuff. But out of response for a new type of course that you'll see today that sort of gives people an in-depth understanding of systems, but more from a high-level or programmer's perspective. And we'll talk some about the philosophy of the course later. So this book, as you saw, just came out its third edition last March, and that's the required text for the course. And there is nothing you can do to avoid buying that book. And it's not because we're greedy. Actually, we take the money we get from royalty for students in this course, or any CMU course, and we donate it to CMU. So we're not actually making any money out of you buying the book. But it's a simple reality that the new version is different than the old. We expect you to be using the new version. There are no electronic copies. There are no pirated versions, so you basically have to buy the book. But
I think I was looking for something here. Course overview, contents, discussion, Nothing there. Results. I was searching for something, I guess. In the recording. Okay. And he's got slides down here. Got slides here. Screen. Camera. Oh, there's a camera view. This is pretty high production quality here. How did it skip ahead to 28? Is that because I clicked on the wrong thing? Must have clicked on one of these things. So I'm just getting familiar with the navigation of the little web app here. It's actually kind of nice. Okay, I'm gonna bookmark this as well, just so I don't lose track of it. Okay.
Everyone, I'd like to welcome you all to this this term's instance of this course is officially either 15213 from computer science or 18213 from electrical and computer engineering. But a large number of the people enrolled in this course are in one called 513, which is for graduate students. And to be totally honest, you're not supposed to. I don't really know who you are. Students on campus enrolled. Try that. That's better. So my name is Randy Bryant, and my co-instructor is Dave O'Halloran, and those names might be familiar if you have been to the bookstore, because the book was written by us. And we actually wrote this book. We started 213 as a course in 1998. And I know that you were children then and all that stuff. But out of response for a new type of course that you'll see today that sort of gives people an in-depth understanding of systems, but more from a high-level or programmer's perspective. And we'll talk some about so this book, as you saw, just came out its third edition last March. And that's the required text for the course. And there is nothing you can do to avoid buying that book. And it's not because we're greedy. Actually, we take the money we get from royalty for students in this course, or any CMU course, and we donate it to CMU. So we're not actually making any money out of you buying the book. But it's a simple reality that the new version is different than the old. We expect you to be using the new version. There are no electronic copies. There are no pirated versions. So you basically have to buy the book. And I don't really apologize for that, because I know you or your parents or somebody's paying a lot of money for you to be here. And so the price of the book is really a relatively small amount relative to that. And this course, by the way, is not, some courses there's, oh yeah, this book, you might want to look at it once in a while, but actually the course has nothing to do with it. This course, the book and the course are one. They're very tied together. There'll be parts of the book that we don't go into all the details that are in the book sometimes, but we expect you to be able to figure it out. And so really, the course and the book are tied together, and they're very much the progress of the course, the topics covered, how it's covered, everything about it is consistent with the book. And we wrote the book because of the course. Think of them as course notes. So, and the reason why we are teaching this term, by the way, we haven't taught together in several years, but because this is the first rollout of this book, and not only is it being used here, but it's actually used by about 250 schools around the world, and many of those people are also going through the same activities of teaching for it from this new edition for the first time. And so we wanted to make sure all the material for the course was sort of put in order and things, because other universities and other colleges use this material, the supporting material we've developed. So that's the course. And today is the first lecture. We're sort of doing a tag team here. I'll talk the high level what the course is about, what the main themes are, and Dave will talk more about the logistics. So we refer, the saying we have, when the very first time I typed the number of this course into a text editor, I realized I've typed those 5 digits many times in my career because it's the zip code of CMU 15213. So that's where we come up with the saying. So there's a few things about this course. For the most part, you know, in your normal undergraduate curriculum, when you've learned programming, you've been very much separated from the realities of the machine. You just think about code, you put some text into some little box somehow and outcomes of behavior that it hopefully is what you intended the program to do. The purpose of this course is to give you enough understanding of what that box is doing when it executes your code. And through that, to help you become better at what you're trying to do. So some of the outcomes is, there's really 2 types of outcomes from this course. One is that if this is the only systems course you've ever taken your whole life, you will get useful material from it. You will learn tools, tricks, methods that will help you if you ever are involved in software development, large-scale software engineering projects, systems, hardware design, any aspect of computer technology. This will help you be better at what you do. You'll understand what programs do, how they work, what the machines that support them do, why sometimes they work really well, and why sometimes they don't work so well. It also is intended as a sort of stepping stone into a whole number of other courses at CMU that will give you more in-depth understanding of computer technology, but are sort of specialized by topical area, whether it's computer networking or operating systems or embedded systems, where you'll take the sort of ideas from this course and be able to then learn in a somewhat narrower but deeper sense what's really going on. And so it really is trying to serve those 2 goals of making you more effective, giving you useful ideas and tools right away, but also preparing you for later courses. So one way we talk about this is sort of what kind of stuff will you learn from this course is to go through a series of what we call great realities, places where sort of computers meet up, real-life computers meet up against your expectations, and maybe they're not quite the same. So one of them is, in the first part of the course, is going to take a fairly detailed look at how numbers are represented in computers, and you'll learn some things that are, on one hand, surprising, and on the other hand, will start to make sense when you understand it better. So a simple case is, for numbers, I don't know when it was but it was probably in about 8th grade algebra that I learned that if you square a number, it will be at least 0 if it's not an imaginary number. So either an integer or a real number, you'd expect to square it and it to be a positive value or perhaps 0, right? And that's actually generally true with floats, the representation of floating point numbers. But with integers, or ints, the computer representation of integers, it's not so clear. So for example, if you square 40,000 on most computers, then you'll get whatever that should be, as you'd expect. But what if you square 50,000? So you could do this in your head, but actually built into this laptop is a computer, so I'm going to go ahead and use it. And use a tool, which on Unix systems is called, no, it's called on Linux systems, it's called GDB, but on a Macintosh OS X, it's called LLDB, but they're pretty much the same program. You will get to know this program really, really well this term. So like I said, if you square 40,000, you'll get what you'd expect. But let's change this to 50,000. And you get a very peculiar number that doesn't look anything like you'd expect 50,000 squared to be, and in fact, it's negative. And so that might just seem like, well, there must be a mistake or something. No, that's just the way it is, because this computer is expecting 2-bit values. And the bit pattern that you get when you do this multiplication.
Let's go ahead and make sure we have LLDB installed. Nope. Pacman search LLDB. Yeah, let's go ahead and install that. And then, oops, LLDB. You can just print, was it 40,000 times 40,000? Oops. It's not what I wanted. I'm on this like new keyboard which has all the keys really packed in tight, and so if I hit backspace, if I miss it, I'll hit print screen. I would like to enable the Vim mode in LDB. In LDB, can I enable Vim key bindings? Vim? Huh. It's just hallucinating shit now. Feels like ChatGPT is just like barfing up garbage here. So LDB, so you can pass a REPL. That's annoying. Just barely wraps. Okay, let's just look at some of the things here. So you got I'm looking for a way of like maybe I can pipe in echo settings list into LDB. LDB settings list. Maybe it needs a new line. I guess echo would have come with a new line. What if I do this? Say, hey, echo settings list, and then just sleep for 2 seconds. Huh. Alright, since ChatGPT's on the fritz here, let's ask Gemini. In LDB, first, how do I run commands and then exit, capturing the output of the command? Execute specific LDB command. Okay. LDB O settings list. Okay. And batch, I guess, puts it into like a mode where it doesn't keep on running. And then we can grep for editor. Is it possible to enable Vim mode inside of, say, key bindings inside of LGB? That's a bummer. Huh. I'll be back. Give me 1 second. Okay. With what? Edit RC. Okay. Edit RC. Bind V. And then we LDB here. Yeah, no target's fine. Hey, look at that. Just GDB now? Nope. Okay. any CLI utility in a readline layer. I don't know about that. Cool. The dot edit RC change worked. Can you do the same for GDB? Vim dot input RC set editing mode VI GDB test. Hey, look at that. Great. So now we got Vim mode and GDB and LDB, which is essential, absolutely essential. So he's doing what, 40,000 times 40,000. Then if we go here, we go negative. Cool. Thank you, Gemini. You're way better than ChatGPT. Kill that. Where are we at? Where are we here? Alright. And stop clicking on the links, Canoe. Alright. How did we even get over here? What even is this? What is going on? Alright. So we're on 3. Okay, move B back over there. Okay, great. And I'm just going to do you there for now. Alright, let's continue.
Number. So that's an example of where your normal expectations about integer arithmetic may or may not hold. On the other hand, there are some places...
so bright.
Like if I try to do the same thing, multiplying 300 by 400 by 500 by 600, then all of a sudden I also get a number that clearly is not what you'd expect, because the same thing has happened. I've gotten an overflow. It happens that it's overflowed. It still is obviously not the integer product of those 4 numbers. On the other hand, one thing you'll find is, even though this arithmetic is not normal sort of integer arithmetic, it actually has some well-behaved properties. So for example, if you look at what I've done is I just the beginning, and so that's an example of where your normal expectations about integer arithmetic may or may not hold. On the other hand, like if I try to do the same thing, multiplying 300 by 400 by 500 by 600, then all of a sudden I also get a number that clearly is not what you'd expect, because the same thing has happened. I've gotten an overflow. It happens that it's overflowed to a value that's positive, not negative, but it still is obviously not the integer product of those 4 numbers. On the other hand, one thing you'll find is, even though this arithmetic is not normal sort of integer arithmetic, it actually has some well-behaved properties. So for example, if you look at what I've done is I just moved the 300 around from the beginning of the product to the end of the product. And so now if you think about how associativity and commutativity works, I'm basically multiplying these 4 numbers in a different order. But what you see is you get the same funny-looking result no matter how you do it. So what you can say from this is integer arithmetic is commutative and associative. So it obeys some of the conventional mathematical properties. It just isn't what you'd expect it to be. It's not a normal sort of mathematical integer arithmetic. So the cartoon here shows an example that's a similar possibility. Let me get to it. Oh, I guess it comes at the end. So the next question is addition associative, right? Can you order the numbers? And as you probably might have figured, both the integer arithmetic, even though it has this potential for overflow, it is associative, and it's commutative too. But for floats, it's not really quite the same, because the range of values you can get in floating point are so extreme that some numbers kind of disappear on you. So the example I'll show without having to use a computer to do it is if you take a big number and subtract it from itself, you'll get 0. So if you add that to 3.14, you'll get 3.14. But if you take those 2 numbers and you reorder how you combine them so that 3.14 compared to minus 10 to the 20th is so insignificant that result gets turned into minus 10 to the 20th. And you add that to 10 to the 20th and you end up with 0. So it's not associative. And so what you see is both these number systems have some peculiarities, and it all comes down to the fact that they use finite representations of things that are potentially infinite in their expanse. And so there's some compromises in how those work. And what the compromise is, you can overflow an integer and run out of room. And in floating point numbers, you have round-off problems where you sort of drop the digits that aren't significant. You can also overflow floating point, but the more common problem is round-off. So this is shown in this cartoon, this idea of overflow of somebody counting sheep, which in the US is, or in English language at least, a way to fall asleep. And when he or she goes from 32,767 and then increments that by 1, gets minus 32,768. And we'll see exactly why that happens. But basically, the numbers are going up to the largest value it can represent, and then when it goes 1 more, it becomes a negative number. So these are really important things to understand. I mean, 90% of the time, maybe you can just get by writing programs and not worrying about whether your numbers are going to exceed their possible range. But there's sometimes when this could be really important. If you're like controlling a rocket, you really don't want the positive thrust to become negative or something like that. So you can see this could be an important consideration. Similarly, there's well-known instances of security vulnerabilities where somebody wrote code that sort of expected a positive number in some place, and a clever person figured out if I supply a negative number, I can fool the system and get it to do bad things. So these are the kind of corner cases that you need to understand better if you're either working in programs where it's really, really important that it work correctly, or you're really worried about security vulnerabilities. Anytime you have possible for corner cases, you have to understand these nuances better. Similarly for floating point, if you're going to use floating point for serious computation, whether it's scientific research or for designing bridges or nuclear power plants or something, you better understand what the characteristics are. So that's our first one, and we'll spend a couple weeks talking about numbers and number representations and their properties here. The second is we're going to spend a lot of time in this course learning about machine-level programming, meaning what the instructions are that actually get executed by the computer. And that can be described in assembly language, which is a text version of it, or in object code, which is the actual bit-level binary encoding of instructions. And we'll learn a fair bit about that and spend a fair amount of time seeing how code that you write in C gets turned into machine code and how that gets executed on the machine. One thing I'll say is that historically, courses like this would teach assembly code by having you write programs in assembly that do various things, not usually very interesting because it's a lot of work to write an assembly program. This course is much more about taking the assembly code that's been generated by a compiler, a C compiler, and looking at it and understanding it. And that's a different set of skills than you need to write it on your own. And in particular, we're going to look at the language of Intel processors. The most recent versions of them are called x86-64, the 64-bit version of their instruction set. And one thing that's new in this course compared to previous ones, we used to teach 32-bit stuff. This course is 64 bits all the time.
Doesn't seem like he's covering everything in the slides, so let me read over the slides before he advances. So the first one, the great reality was, where is he? Ints are not integers, floats are not reals. So they behave a little bit differently. They overflow, they underflow. They have some properties of associativity and what's the word? I just used it today. We can reverse the order of the operands. Commutability, is that what it is? I figure I should know this from grade school. Associativity versus commutativity. It's commutative. So integer arithmetic is associative and commutative, but it may come up with a bad result. Floating point numbers do not have associativity in general. Computer arithmetic does not generate random values. Arithmetic operations have important mathematical properties. Cannot assume all unusual mathematical properties due to finiteness of representations. Integer operations satisfy ring properties. Commutativity, associative, distributivity. I've never heard of that one. Floating point operations satisfied ordering properties. Monotonicity, value of signs, observation. Need to understand which abstractions apply in which contexts. Important issues for compiler writers and serious application programmers. Let's go ahead and ask ChatGPT, even though it's been messing up. What is distributivity in the context of math? Probably describes how one operation interacts with another. Most commonly, it refers to how multiplication distributes over. Oh, okay. It's been a while since I've done any algebra. Yeah, distributed property. Cool. So he talked about great reality 2 here. You've got to know assembly. Chances are you'll never write programs in assembly. I wrote a program earlier in the year in assembly. It's a trivial one, but still write it. There's this new assembler that I heard about. It looked pretty cool. I forget the name of it. So that's ChatGPT if it knows. What are some names of assemblers? Ideally ones that are currently being developed and maintained. Yeah, search the web. Flat assembler. I think that's what it was called. Yeah. FASM. Flat assembler. Is this it? Yeah. Yeah, and this is the web server. It's competing with Nginx. Let's check out the GitHub. FASM. Wow, so it's kind of an old one. I didn't know that. Can you just show me the text, please? I don't want to download a freaking zip file. Look at those transitions. Is that some type of like CSS fancy shit? I don't know. It's something I heard about. I don't think I would ever use it. I think NASM is the only assembler that I've used in the past. Behavior programs in presence of bugs. High-level language models break down. Tuning performance. Tuning program performance. Understanding optimization done, not done by the compiler. Understanding sources of program inefficiency. Implementing system software. Compiler has machine code as target. Operating system must manage process state. Creating, fighting malware. x86 assembly is the language of choice.
A couple weeks talking about numbers and number representations and their properties here. The second is we're going to spend a lot of time in this course learning about machine level programming, meaning what the instructions are that actually get executed by the computer. And that can be described in assembly language, which is a text version of it, or in object code, which is the actual bit level binary encoding of instructions. And we'll learn a fair bit about that and spend a fair amount of time seeing how code that you write in C gets turned into machine code and how that gets executed on the machine. One thing I'll say is that historically courses like this would teach assembly code by having you write programs in assembly that do various things, not usually very interesting because it's a lot of work to write an assembly program. This course is much more about taking the assembly code that's been generated by a compiler, a C compiler, and looking at it and understanding it. And that's a different set of skills than you need to write it on your own. And in particular, we're going to look at the language of Intel processors. The most recent versions of them are called x86-64, the 64-bit version of their instruction set. And one thing that's new in this course compared to previous ones, we used to teach 32-bit stuff. This course is 64 bits all the time.
Memory matters. Random access memory is an unphysical abstraction. Huh? Oh, because of all the caching and stuff that goes on, it's not really like truly random access. Because that's what he's saying. Memory is not unbounded. It must be allocated and managed. Many applications are memory dominated. Memory referencing bugs, especially pernicious. Effects are distant in both time and space. Memory performance is not uniform. Caches and virtual memory effects can greatly affect program performance. Adapting program to characteristics of memory systems can lead to major speed improvements.
fair amount that is really fairly visible to programmers, surprisingly visible, is aspects of the memory system. So modern computers have a very complex layered memory system to try and give you high performance and high capacity at the same time. System that can mean that if you write a program well, it might work really well, and if you don't, it could run very poorly because it's not making use of this hierarchical memory system. So, and also, there's a lot of bugs that show up, especially in C programs, that have to do with memory referencing errors. And so understanding what those errors are, what their manifestation is, how to prevent them is a big part of the course. So for
memory referencing bug. Excuse me. Type def struct, anonymous struct. I don't know why people do this. They do a type def, and then they have the struct, but you could just give it a struct tag. I guess people don't like using the struct keyword. Let's see if ChatGPT can do this. Break down the following C code into grammar nodes. Is that how you spell grammar? Grammar. I thought it was a, yeah. Let's do type def struct foo. Foo t. And here we'll say boop 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 int a2 boom. I wonder if like if people saw how their programs were being parsed into an AST, if they would affect how they write software. If you saw the data structure that was generated. So storage class specifiers. The type def is a storage class specifier. Yeah, I was just curious about the parse on something like that.
two integer values a.
So we didn't actually look at what he was doing here. So he has a struct that has an array of two integers and a double D. He declares the struct as volatile on the stack of this function fun that takes in an I. He then assigns into D 3.14. He assigns into A sub I, which I might be 0, 1, 2, 3, it doesn't matter. So it could be possibly out of bounds, this big number. And then you return SD, it could be clobbered. That's the idea there.
Point number D. And if I, this function, fun, you'll see what it does is it's given an argument I, and it sets the ith element of A to some strange looking value. So, as you know, I should really only be either 0 or 1 with this code, because that's the range of possible values of this array A. But
you gonna crash on me? I believe in you, come on. Did I lose internet? I'm not, I'll do it. I'm still up. Well, 2006 is where we left off. Let's hit a refresh on this bad boy. 2006. Close enough.
in particular, if you run it on either 1 or 2, you'll get what you'd expect, that you assign 3.14 to element D of the structure, and when you read it back, you get the same thing. And in fact, but now if I set A of 2 to this number, all of a sudden you'll see that my floating point number, which seems to have nothing to do with A, has changed. And if I do that same thing with I equal to 3, you'll see I get a number that's closer to 2 than to 3.14. And if I keep going, well, nothing much happens until I hit 6, and then the program crashes. So something interesting is going on here, at least something quirky is going on. And the reason is, again, it has to do with how data is laid out in memory and how it's accessed. And one of the features of C and C++ is it doesn't do any bounds checking on arrays. It will happily let you.
All right, well, let's go back here. So why did function 2, fun of 2, only slightly perturb the value, whereas fun of 3 completely destroyed it, and then fun of 4 didn't touch it at all? Probably because it's integers being assigned into a dead space at that point. Double D, I think double on a 64-bit machine is how big? Double, I think it's 64-bit. Let's pull up our K&R book. So we have a program in here that we wrote. I think it's chapter 1. Build, make, build, test, int sizes. So it's 64-bit, yeah, doubles 8. So you got 2, and then you got 2 bytes of padding for alignment, and then you got your 8. Let's see what he says.
Something quirky is going on. And the reason is,
so he says it's packed in here, but I don't think so. Maybe on a 32-bit machine, the packing might look like this. Because on a 32-bit machine, a double would be 8 as well. So 8, it's always going to be 8, but you can be 32-bit aligned on a 32-bit machine for 8 bytes. You don't have to be 64-bit aligned. So when you pull that in, that means that it still would be 0, 1 would be the array, and then 2 and 3 would be not use padding, and then 4, 5, 6, 7 would be, and further up to 12 would be your size of this, because your double is going to be 8 bytes regardless. But I don't know what type of machine he was running on. I guess we could jump over to our what do you want to do? Let's jump over to our CS app. And we're just going to rsync over from K&R chapter 01. We're just going to rsync that whole thing here. And then we're going to go into chapter 1 and make clean it. What does count do? Oh, and I did a histogram too. Forgot about that. Don't care about that. Did I do a histogram? I didn't realize it did a vertical and horizontal histogram. I forgot about that. RM test EOF def. RM test extern. RM test no args. RM test old style func. So we're just left with this compare stuff. I'm gonna vim up makefile and expanded. Why is that even a thing, expanded? Oh, I wanted to do a macro expansion test. That's why I had that there. We need our I like doing standard C23 since we have it. And why don't we do that for this as well? But this, of course, is not going to get target set. It's a different set of flags. Okay, that looks good to me. Oops. Can you please right click all? Compare. Okay, this is the comparison. So basically it's longs. Long double, long int, long double, and long complex are all different sizes. So what are we going to do here? We're going to test this thing here. Vim test. Fun.c, and I'm just gonna read in my other test just to give me the. Well, I don't need this, but I do want these. Let me just delete all this. Cool. And in here we're gonna have our fun, which is double fun, takes in int I, and we have our struct. He did type def struct. What is this thing called again? A struct t, and inside here was a int array of 2 elements and a double d. Oops. Okay, and then over here we allocate our struct t s, and then he initialized the s.d to be equal to 3.14, and then he did s.a sub I to be equal to I think it was I. What did he have it assigned into? Oh, some actual integer value. 10, 7, 3, 7, 4, 1, 8, 2, 4. Okay. And then we return s.d. And he labeled this as volatile. Which basically means don't optimize it away. Is volatile. Okay, and then over here, what are we going to do? We're going to call our fun. Say for auto I is equal to 0, I is less than, what is this, 32, I plus plus. And then I'm going to do it the C way, trying to get used to this. So we say fun of I. And we want to print this, so printf out fun of I. And we give it a format string, which is going to be %d. It's not going to be d. F? New line? Yeah. Oh, and we need to update our Vim. We need to get our ClingD stuff. knrc. Fine. ClingD. CP chapter 08. ClingD into CS app chapter 01. ClingD. Yep. Vim test fun. There we go. Got everyone to behave now. So now we can make build test fun. Hey. Oh, it's because we're using Zig CC. I mean, it's cool that Zig blows up, but maybe we'll trick Zig into not blowing up. So I'm just gonna go back over here, ask AI, hey, can you tell me the Zig CC flag to produce a release build? Release fast. So here we're going to say, hey, O is going to release fast. I gotta give me 1 second. Alright. Let's try and see if this helps. Make clean, make. What? Is fucking ChatGPT just being a piece of garbage? Oh god. Let's try it again. Make. Yeah, it does say oh. I already tried that, idiot. Fucking idiot, man. What an idiot this program is, man. Obviously. Okay, maybe we can get it to... You know what? I'm just going to use GCC for this stuff. Because I don't want any optimizations. I just want to do the thing that the... There we go. Build, test, fun. There we go. That's all I wanted. So again, this now it's starting on this system. Okay, so maybe let's try to get it to work with ZigCC. ZigCC flags. Default undefined behavior sanitization, debug mode, default, or when not using O2 or O3, automatically enables fsanitize undefined for C code. This causes undefined behavior to result in an illegal instruction crash. I think I might be getting sick. Let me turn a light on here. Boop. That's a little bit better. Alright, so we got ZigCC. Can we disable sanitization? F no sanitize. let's see if we can do that and get it to do what we want. So we want O0. We don't want any optimizations. We just don't want all this sanitization crap. Make clean. Make. Hey, that worked. This one crashed immediately after the access, though. Which GCC doesn't. So. And then if we do a 32-bit build on this. And I'll do my F. No sanitize. Undefined. Sorry, messed that one up. This needs to be test fun 32. Test fun.c. Oh, the all needs to be updated here too. So build test fun 32. There we go. Make. So 32 has the same behavior as the 64-bit. This was stack smashing detected. The GCC one was not. It was... No, it was stack smashing detected. So we're basically doing something where we're clobbering the stack. I would like to disassemble this binary and see what it's doing. So maybe do an obj dump and then disassemble and obj dump disassemble symbol d equals. Okay. Obj dump disassemble equals fun. Build test fun. That was not what I wanted. Disassemble. Oh, you have to give it like a flag like that. That makes sense. It seemed like the single flag was not going to work there. Typically doesn't. Disassemble is equal to fun. Okay. So let's try to read through and understand what's going on here. Since this class is all about assembly, jump over to CS app, and we're going to open up our, let's go into chapter 1, open up our test fun, and we'll zoom in here, and I'm going to actually get Godbolt in the mix because it's just so helpful in understanding things. Oh, and I need the struct definition too, of course. In fact, I don't even know if I need the obj dump. I can just look at the output here. So, this is all preamble to set up the argument I. So you push the base pointer onto the stack, and then we take your stack pointer and set it, assign it into our base pointers. This is a standard C calling convention. So now we have our base pointer pointing at the new base of the stack. And at the end we pop, which restores the base pointer to where it previously was located at. So our stack pointer and our base pointer pointed at the same thing here. And then we say, okay, we're going to move EDI, which is our register for our argument here, into -20. Our return here is happening here, which is basically, I guess XMM0 is being used to return. That seems weird. We set XMM0 for a return. Let's go ahead and close this out. I'll close this out for now too. And I want to bring up a. Let's see if there's a registers used in C calling convention. AMD 64 sysv. Yeah. I just want like a whole table of stuff. Like, tell me what all the registers are used for. Maybe this one? No, it's words. Table. Maybe Microsoft, who knows? They might have something. Ooh, look at this little table here. Cool. So that's how they're passed. So fifth and higher, fourth, third, second, leftmost. RCX? I don't think that's. We're using EDI. This is the wrong calling convention. This is X64. Is it X86-64? I think this might be a different calling convention. Linux. This is also called X64. Well, they gave us a table here. So XMM0 you can see is the floating point. Where would be a good reference for this? This guy? Does he have a table? Floating point return values. Floating point return values are returned XMM0, which is what we see here. I just want an easy. I guess AI is gonna have to be my reference now. I wanted an easy reference for like a table that just shows like these are the registers used for different argument types and return types. Okay, so we got a return quad. So that means RBP -8 is gonna be our location for our s.d. So because we declare all the memory for the stack is this S, it has the array 2 and then the D here. So 8 would be the size of the double. And then array 2 would be 2 bytes. 2 integers. Not 2 bytes. Silly rabbit. So an integer on what is this? CS app. CD chapter 1. If we go and do our compare, or I just want to build int sizes. So our int will be 32. So this will be 8 bytes long. Our double is already 8 bytes long. So these are 16 bytes total. And then we have another 4 bytes for our integer here, which is why this is at 20. So we're going from 20 to 16 for our argument. It's getting stored in that part of the stack. And then 8 will be our XMM register. I don't know why we do that. Oh, because it's this, this is the assignment of the value here. So we copy it from this location, indexed by the instruction pointer. I'm not sure how that works, but basically it's somewhere in memory. It's a read-only data section or something. It gets copied from there into our XMM0 register, and then we get copied from there into our stack. So our stuff is on the stack, where the 3.14, and that is going to be 8 bytes that are now written. So you got the 4 bytes from the argument written to the stack, and we got the 8 bytes from the struct D field. And now we start doing something here where we take this D word and copy it into EAX. Why do we do that? CDQE, I don't even know what that instruction is. I'm going to have to look that up. Okay. So we got, what is the CDQE instruction on AMD 64? Convert double word to quad word extension instruction on sign extends a 32-bit signed integer in the EAX register into a 64-bit signed integer in the RAX register. It copies the signed bit to the from 31 of EAX and all bits to the upper half of RAX, preserving the values sign and magnitude. (64-bit signed integer) copies the signed bit 31 of EAX into all bits 32 to 60. Okay. Of the, and so if it's a 0, then it just doesn't, zeros it out. If it's 1, because the value is negative, it just puts 1s in there. So in a 2's complement representation, this effectively extends the amount of bits available for the integer without changing its value. Yeah, so it preserves these values sign and magnitude. Exactly. Okay, so let's think about what's going on here. So we take the value that's currently at this is the integer value that was passed as an argument. We copy that into EAX. Then we extend it to be a 64-bit value. So EX is now RAX. And so we say this is going to be some pointer math here. So how many bits would this be? So an integer would be 4, be in the billions. So that's thousands, millions, billions. So it's gonna be a 4-byte value. But with the signed, yeah, this will fit in a 4-byte signed value. Max value of a 32-bit 2's complement integer. It's gonna be more than that. Yeah, it's in the 2 million area. Okay. So what we do is copy this very large value that requires 4 bytes to be represented. We say, okay, take RAX. Is this left to right evaluation with no operator precedence? Explain this instruction on AMD 64. Yeah. Okay, so it's moving this constant integer value that's encoded in the binary into, what do they call it? Immediate value. This immediate value into this pointer location. And the pointer is computed by okay, so RAX is like, 1, 2, 3. So we expand it. It does have precedence because this will be expanded by 4. So now we got, it's either at 4, 8, 12, 16, those offsets. So 4 and 8 would be valid values. Oh, but then we take minus 16 here. Okay. So if RAX is 0, that means that RBP is minus 16. If RAX is 1, that means that we're at 20, which is where we stored our integer. That doesn't make sense. Oh, because we're going the opposite direction. Okay, so we go down to 16. So anything above 16 now is fair game, assuming positive indices. If RX is 0, then we're at 16. If RX is 1, then we're at 12. So those are both valid values. And then if RX is 2, then we're at 8, which is where we're actually blowing up our value that we use to store pi here, or this d, because that's a negative 8. And we're going to be copying from that into our XMM. So I would think 2 and 3 would be valid values, and then 4 would get you into modifying the base pointer itself. Is that what we see? So when we run this program, let's run it again. Build, test, fun. So my hypothesis is that 0 and 1 are obviously fine. 2 and 3 will be fine because they're writing into the double. So that's 1, 2, 3. 0, 1, 2, 3 should be fine. And then 4 it should blow up. 0, 1, 2, 3. And 2 didn't affect it because, well, I don't know why, to be honest. Probably because these bits match somehow. I bet you if we set 0 bits, I bet you I'd mess it up. So if we go fun, test fun, and I'm just gonna say set that to 0, and because you're doing a sub I, it's gonna be an integer 0. Okay. Cool. Make. Yeah, you see, it did have an effect on it. I didn't think it would have a huge effect, but it's going to have an effect because basically you're eliminating the low significant bits of the float. You got that exponent, and then you got the mantissa, so it's all like, lack of precision that you're taking away from that byte. Whereas this byte, you're blowing away the exponent, and that the little bits that are hanging out that remain are not significant enough when your exponent's 0. Yeah. What is if we take we'll just say 2 to the power of x. So when your exponent is 0, That means your value is 1. Exponent is 1, your value is 2. To actually get to 0 from the exponent would be, well, I guess you can't, because it just approximates to 0. Well, suffice to say, you're getting very close to 0, and it probably just rounds down when you're representing it, because the precision bits on a 64-bit float are probably somewhere over here, and they're insignificant. Okay. All right, that all makes sense to me. Cool. I'm glad we did that. Stepping through the assembly, I think, is something I want to get in the habit of doing more, feeling confident doing it. Godbolt is a godsend in being able to figure out what is actually being generated.
So something interesting is going on here, at least something quirky is going on. And the reason is, again, it has to do with how data is laid out in memory and how it's accessed. And one of the features of C and C++ is it doesn't do any bounds checking on arrays. It will happily let you reference element number 5 million of a 2-element array and not complain, but the operating system might complain, as it did here. And in this particular structure, and we'll see more about how structures are implemented and laid out, but basically if each of these blocks in this vertical chain represents 4 bytes. And so the 2 elements of A each are 4 bytes. D is 8 bytes, and then there's some other stuff in the other beyond there.
Yeah, I think this is right. 4 bytes, and then we were at 16, so that's going to be, yeah, we're going to be talking about overriding the base pointer at that point.
So you'll see that if I reference either A of 0 or A of 1, then I will just design. But when I'm calling fun of 2 or fun of 3, what I'm actually doing is altering the bytes that encode this number D. And that's why you saw the sort of funny numbers come out of it. And as I go up, at some point, when I hit 6, I'm modifying some state of the program that it's using to kind of keep things organized, most likely how it keeps track of allocated memory. And that's causing the program to crash. So this is a pretty good demonstration of why C programming can drive you crazy. Because as you saw, it doesn't do bounds checking. So it's easy to write code that does invalid stuff. It's also often the case that you'll cause some problem, and it has a sort of action at distance feature that you can modify think you're modifying some data structure, and what you're doing because of the way things are organized in memory, you're changing something totally unrelated somewhere else in the program. I mean, imagine they're not just 1 apart, but they're 10,000 apart. And things might just run fine for hours, days, or weeks, and then all of a sudden, at some point, that data that got corrupted a long time ago gets accessed, and something goes wrong. So this can be some of the worst debugging nightmares that exist on Earth, is to try and figure out memory referencing errors. So this is actually one argument not to program Earth time ago. Things might just run fine. You're changing the distance, solid stuff. You crazy. Because the program to crash. So this is a pretty good demonstration of why C programming.
Okay, memory referencing errors. C and C++ do not provide any memory protection. Out of bounds array references, invalid pointer values, abuse of malloc and free, can lead to nasty bugs. Whether or not bug has any effect depends on system compiler. Action at a distance, corrupted object logically unrelated to one being accessed. Effective bug may be first observed long after it is generated. How can I deal with this? Program in Java, Ruby, Python. Okay. Understand what possible interactions may occur. Use or develop tools to detect referencing errors.
Because as you saw, it doesn't do bounds checking. So it's easy to write code that does invalid stuff. It's also often the case that you'll cause some problem, and it has a sort of action at distance feature that you can think you're modifying some data structure, and what you're doing because of the way things are organized in memory, you're changing something totally unrelated somewhere else in the program. And imagine they're not just 1 apart, but they're 10,000 apart. And things might just run fine for hours, days, or weeks, and then all of a sudden, at some point, that data that got corrupted a long time ago gets accessed, and something goes wrong. So this can be some of the worst debugging nightmares that exist on Earth, is to try and figure out memory referencing errors. So this is actually one argument not to program in C or C++, and it's a valid argument, I'll admit. But the person who's writing a lot of C programming, you just get more experienced, and you know at times that you should actually put bounds checking in your own code. And there's also tools available that will help you sort of bulletproof your code so that it will detect these kind of problems. So it's not like you have to change languages, but it is a particular feature of these languages. And so presentation of data structures and how they work really makes a huge difference in your ability to deal with these kind of vulnerabilities and things. Vulnerabilities, by the way, also from a security perspective. The fourth sort of theme we'll cover in the course is getting performance out of programs. Other parts of the curriculum in CS do much more emphasis on getting the right algorithm or the right data structure. And that's really well and good. It's important stuff. I don't deny it. But there's some amount of the sort of low-level view that you need to understand what the system does, what makes it run well, what makes it run poorly, in order to be able to do that kind of optimization.
Great reality number 4. There's more to performance than asymptotic complexity. Oh, I am very tired. I just had no energy today whatsoever. Okay, there's more to performance than asymptotic complexity. Constant factors matter too. Yeah, of course they do. Sometimes taking a constant factor out of an algorithm is like a huge win. If it's a big constant factor. And even exact op count does not predict performance. Easily see 10 to 1 performance range depending on how code is written. Must optimize at multiple levels: algorithm, data representations, procedures, and loops. Must understand system to optimize performance, how programs compiled and executed, how to measure program performance and identify bottlenecks, how to improve performance without destroying code modularity and generality.
These two functions do exactly the same thing in terms of their behavior.
Oh, yeah.
What they do is copy a matrix
Row versus
array
column access.
called source or SRC to a destination DST. They're both sized to be 2048 rows, 2048 columns, two-dimensional arrays. And you'll see that the programs do the obvious thing. You have a nested pair of loops to do the row and column indices, and you just copy from one source element to a destination element. The only thing that's different, you'll see, is that the two loops, their nesting is different. The nesting order is different. In one case, I'm going kind of row first, going through all the rows, and then the columns, and the other is for any given row, I'm copying all the columns. That's really the only difference between these two programs. But what you'll find if you run it on a typical system is that one is much faster than the other. In this particular machine we ran it on, it was about close to 20 times difference in performance. So something fishy is going on if the same program that differs only in a seemingly insignificant way, a way that has no effect whatsoever on its functionality, can have this much performance difference. And so to understand this, you need to stare at the cover of the book. Because basically, to understand this, you need to stare at the cover of the book. Because basically, you're at two different points of this strange-looking picture that's on your book, and since there's no axes or labels on it, it makes no sense whatsoever. But it's there. So what you see is this picture shows for different memory access patterns, and I won't go into the details, what the throughput measured in megabytes per second on basically a copying program was. And without going into the details, what you'll see is these two functions sort of sit at different points in this memory access pattern. The one that goes through row by row is much better than the one that goes through column by column. And as a result, you're getting a lot better performance, and it has to do with this memory hierarchy and what they call the cache memories, that you're getting way better performance out of it in one case than the other. So that explains what the cover of the book is about, and we'll talk about it more later in the course. And then the final part of the course talks more about not just getting computers to run little programs in isolation, but getting computers that talk to each other over networks and implement services like web servers and other functions like that, which of course is where most of the world of computing sits today. It's not just isolated machines, but computers that interact with each other over the network. They're embedded controllers that are interacting with the physical world. So really, the world of computers is a much richer environment, and we'll cover at least some aspects of that in the final part of this course. So as I mentioned, the other feature of this course is it will get you ready for other systems courses you might take at CMU. And here we've listed actually a subset of the courses at the university that require this course as a prerequisite. And they're mostly in computer science and ECE. But you'll see it's quite a range of different courses. And each of them builds on sort of one or multiple aspects of the material you learned in the course. So the reason why we make everyone take this course, including incoming master's students, is that all these other courses at the university have come to rely on students being familiar and having done the work of 213 or 513 as a prerequisite. And they can build on that material and sort of cover more ground as a result, rather than having to do what would otherwise be somewhat remedial work on it. And in fact, part of the genesis of this course was the people who taught the operating system course, 410, sort of complained that they were spending too much time at the beginning of the course talking about some very basics of machine programming. And Dave and I said, oh, well, we can cover that. So that was part of what got this course started. Has a sort of perspective that's very different from traditional systems courses. Most systems courses, including that whole array you saw there, were about how do I build some particular feature? How do I implement an operating system? How do I design a pipeline microprocessor? That's all important stuff to know. We really want the people who are out there building operating systems and designing microprocessors to have learned how to do it. On the other hand, as a way to sort of get the experience.
Most systems courses are builder-centric: computer architecture, design pipeline, processor and Verilog, operating systems, implement sample portions of operating systems, compilers, write compilers for simple language, networking, implement and simulate networking protocols.
Perspective, meaning understanding what you as a person who sits in front of a computer screen and types code need to know about that machine you're typing code for in order to be effective at doing it, as opposed to somebody who's someday going to be designing the actual machine itself. So that by taking that perspective, it gives you sort of an understanding. So now when you go off to implement it, you'll actually know what these features are and why it's important to implement them well. But also, by doing this programmer's perspective, it lets you right away get tools that you can use in other places where you're writing programs or doing anything related to it, and be more effective at that. So this programmer's perspective really gives this dual benefit to it that we feel is very useful, and students who've taken the course in the past have expressed that as well. So as I mentioned, we have 2 instructors for the course, and they also happen to be authors, and the longest, we probably taught this course more than anyone else, but it's also taught by other people on campus as well. So what I'm going to do now is hand my pair of microphones over to Dave. All right.
There's enormous demand for MS students for 2 and 3. Okay. Yeah, okay, it's just like
welcome. Good afternoon. Great to see you. My name is Dave O'Halloran, and I'm just delighted to have the opportunity to be one of your instructors this term. This course is one of the reason I'm so excited to be teaching this course. I mean, I just love this course. And O'Halloran, and now is hand my pair of microphones over to Dave more than anyone else, but it's also taught by other people on campus as well. So what I'm going to do now is hand the course's opportunity it represents to have an impact on people's lives. We really believe that the material you learn this semester can have a really positive and long-lasting impact on your careers. And it'll help you not only with your future classes, but also future positions you have. And I hear this from people all the time, former CMU students and students around the world who have taken the equivalent of 213 at their schools. Even a couple years ago, we were interviewing a faculty member, a tenure-track faculty member, who went to did his undergrad at CMU, and then went off to Stanford, got his PhD at Stanford, and was coming back to join the faculty. And he told me that 213 changed his life in our interview. And I don't know if he was trying to butter me up, but I think I believe him. He said it changed his research direction. He didn't really know what he knew he kind of liked computer science, but he didn't really know what direction. 213, he knew that he wanted to do his life's work in systems. Now, it was just remarkable, right, to come back, and we ended up actually hiring him. And he told me that everybody in his lab at Stanford, all of the grad students, had a copy of the book on their desk. And they were from all over, all different schools. And so, I mean, I was in a bookstore in Beijing a couple years ago, right outside the BKU campus. And I was up on the 5th floor trying to see if I could find a copy of the textbook. And I found the English version in one aisle. And then a couple aisles over, I found the Chinese version. I was going through the Chinese version, and this guy taps me on my shoulder. And I turn around, and he says, "Oh man, that book is really good. The English version is 2 aisles over." And I mean, it just blew me away to be in the head of someone like halfway around the world. It was just one of those moments. And so I'm not trying to boast. I'm just trying. I want to give you the sense of what an opportunity this course represents for Randy and I to have what we hope will be a really positive impact on your lives. So let me. We have kind of a funny organization for the course in response to the tremendous demand we have for it. So there's actually 3 course numbers, but it's all the same course. Okay, it's identical course. 513, 15, 513 is for our master students, and make those available. Have enough seats.
I'm going to skip over this just because it's
okay. And
college.
The undergraduates will go through lectures and recitations. Okay.
Sorry, it's Carnegie Mellon computer science department stuff. It's not really relevant to the material.
In person, graduate students will watch videotapes of those. But otherwise, yes. Yeah, we're making them available to everyone, actually. Sorry? And lecture slides as well. Everything's available on the course webpage. So you'll be doing, all students will have equal access to office hours, the staff mailing list, and everybody does the same labs and the same exams. Okay, so it's just a matter of whether you go to lecture in person or if you watch it on video. In fact, since it's available to everybody, if you miss lecture, it'll be there on the webpage and you can catch up, which I know you'll probably do. Actually, I know most of you will never miss class, right? But the few of you who do, you'll be able to watch it. I love teaching, but this is the one part teaching that notions of academic integrity and different notions of cheating. Searching the web courses is public reading, and I just the class high level using kind of the way if day 2 and then 4. You don't want. So there's plenty of opportunities and ways to get help. Start early. And you go to of supporting material on the book's website at csapp.cs.cmu.edu. And as Randy mentioned, this book really matters for the course because actually the book came out of the course. Right? So the book is the course is the book. And so it'll really help you. The labs that we do come directly from material that we discuss in the book. So what I would encourage all of you to do, and I'm not sure if anybody has ever taken this advice, but I say it every year anyway because I believe it. But I think a really good strategy for studying and preparing for this course would be to read each chapter 3 times. Read it 3 times. Work and practice problems. So we have littered throughout the book of practice problems with solutions at the end of the chapter. And these practice problems are like little sort of bite-sized morsels just to kind of check your kind of sanity check of your understanding of the material. So I think if you read the book each chapter 3 times and work the practice problems, that would be an excellent way to go through the semester and prepare. The other book we use is the Carnegie and Ritchie's classic C programming book. I think this was written a long time ago. It's still the best book around, I think, for C. It's a beautiful example of technical writing. It was one of the inspirations I used when I was writing the book. I tried to find the same clarity and precision that Carnegie and Ritchie had in their book. So this is a really good book. I mean, this is the kind of book, it's a reference, but it's the kind of book you can just read from beginning to end and get a really good understanding of C. There's 4 main components to the course. There's lectures where we go over the high-level concepts, recitations, which meet once a week for an hour, led by recitations is really to help you with the labs. So it's very practical and hands-on.
There's 7 of those labs, and these are really the heart and soul of the course. This is where all the real learning comes in, I think, when you actually have to do this stuff. And that's why we take the cheating part so seriously, because if you do these labs, you're going to learn an incredible amount of really cool stuff. If you don't do them, you won't learn anything. One of these labs is 1 or 2 weeks each, and involves typically some kind of programming or measurement. There's also 2 exams, a midterm and a final. The exams are proctored, they're online, proctored in Wien and Gates. And what we do for the exams is we take like 4 days from 10 to 10, and then you can sign up, and then we have like multiple clusters that are network isolated, and then you can sign up for a slot, like a 6-hour slot. And the midterm is like nominally like an hour, 80-minute exam, right? It's the same exam we gave when we used to have people sitting in person. So it's nominally like 80 minutes, but we give you like a 5 or 6 hour window to do it. Okay, so there's so you can sign up anytime, any day that there's a slot. Okay, so there's flexibility, so you can kind of tailor it to your schedule. And I think we've also removed all the time pressure, right? So which is you can go back, you can check your work, you can just kind of relax and not be worried about how to do it. Now, there's many different ways to get help. The main source of information is the course webpage. That's www.cscmu.edu/213. And all the world can make up. So there's so many people. The advantage is that same exams, every assignment, every lab is a single person, so we don't have any group projects. Where you probably use it for some of your other classes, but the exams like what usually over with, but they're available. So being the same way, I guess we started using Intel machines. Machine. Just great. So this is the part. If you're here, we want you to be attentive and engaged. Your presence in lectures and recitations is voluntary, so we don't take role in either of those. We encourage you to pay the scale. It's required, and no recordings of any kind except this one. Okay, the exams and labs are weighted equally, 50%, midterms 20, finals 30, and final grades are based on a straight 90, 80, 70 scale. Now, rough outline of the semester. The first 3 labs cover programs, machine representations of programs and data. Data lab is how we teach you about bit-level representations of data. So you'll solve a collection of puzzles in C. Like a puzzle might be is a little function that you have to implement, like absolute value. So a function that returns the absolute value of its input argument. The kicker is that we restrict the set of operators that you can use, and it has to be straight line code, no conditionals or loops. And so to solve these puzzles, so imagine how you might try to solve absolute value without using an if statement. Right? The normal way to do it would be if x less than 0, return x, or negative x. Right? See, I told you we make mistakes. Right? But imagine how you might do that without using conditionals and only using bit-level C operations. Right? So this is our way of teaching you how data is really represented in the machine. Now the bomb lab, which you probably heard of, this is kind of famous all over the world now, and at CMU. The bomb lab is the way we teach you how to read and understand assembly language. And a bomb, just briefly, a bomb is a C program that consists of a collection of 6 phases. And each phase wants you to type something into the keyboard. If you type in what it wants you to type, what it expects you to type, then you've defused that phase, and it goes to the next phase. Then you have to type what that phase wants. And if you defuse all the phases, then you've defused the bomb. However, if you type in the wrong thing, then the bomb explodes by printing boom, and you have to try it again. And the kicker is, in either case, if you explode the bomb or defuse a phase, that information gets sent to Autolab. And we use the diffusing string that your bomb sends us, and we check it out on a copy of your bomb that we keep on the server. That's another thing. Everybody gets a different bomb, slightly different bomb. So we check. So when you defuse a phase, Autolab takes the string that your bomb sends us and then compares against the local copy of your bomb. If you explode a phase, you lose half a point. So there's a real consequence to exploding your bomb. It's very, very tense. Right? Until you learn how to use GDB to set a breakpoint before the function that sends the information to the server. And we want you to do that, right? So the bomb's really beautiful. It's kind of fun. It's kind of like a video game. It teaches you how to read compiler-generated code, because the kicker is we don't give you the source code. All we give you is the binary, hence the binary bomb. So in order to defuse a bomb, you've got to fire up GDB, single trace through find where the code is for each phase, single trace through that code, and sort of reverse engineer it and figure out what it wants you to type in. And then you'll quickly find out where that function that explodes the bomb is, and you'll put a breakpoint there. And so we want you to do that because the bomb, besides teaching you how to program assembly language, it also teaches you sort of organically how to use GDB, because you really can't do it if you don't run GDB. And then the third lab is this is a new lab this semester that Randy's developed. It's called the Attack Lab, and we developed this lab specifically for 64-bit architecture. So this is a reflection of the change from 32 bits to 64 bits. And this is really excited about this one. You'll learn how to write exploits using return to a sort of a modern technique called return-oriented programming, which is kind of the modern way that hackers deal with the fact that stacks in newer machines move around and are prohibitive and make it impossible to execute code on the stack. So this is a brand new lab. I think it's really going to be neat. In the memory hierarchy, when we study the memory hierarchy, we have a lab called the Cache Lab, where you'll build your own cache simulator. So this is how you sort of learn how this hardware that Randy was mentioning called cache memory works. You'll build a simulator in C for that, and then you'll take a small transpose function, and you'll try to make that code run with as few misses as possible on your simulator. And this will involve sort of understanding of how the memory hierarchy works and how to exploit it. The sort of transition from hardware to interacting with the system software, the operating system, there's sort of a concept that we call exceptional control flow that exists in all parts of the system, and it sort of represents that intellectual transition from hardware to software. So this is how this was sort of a key idea that allowed us to kind of smoothly move from hardware to software in some intellectually consistent way. And so the ideas that you cover in exceptional control flow are like low-level hardware interrupts and exceptions, and then at the higher level, sort of involving hardware and operating system software, is the idea of a process context switch. And so this is where you start to learn what processes are and how to ask the kernel to create and manage processes for you. At the next higher level, a software form of exceptional control flow called a signal. So this exists solely in the Linux kernel. And then even at a higher level, there's an application C language version of exceptional control flow called set jump and long jump. So this notion of exceptional control flow kind of exists in all parts of the system. We cover it all at once. And the lab that we use to sort of exercise all these ideas is called the shell lab. And in the shell lab, you'll write your own Linux shell, which is really cool. So that's the program, the command line program that you interact with whenever you log into a Linux box. You're going to write your own. And I don't know, for me, that was really exciting when I could write something that looked like a real shell. It was pretty neat. The next area we'll study is called virtual memory. Virtual memory is a sort of combination of hardware and software that presents an abstraction to you of memory as a very large array of bytes. When in reality, memory is a hierarchy of hardware and of cache memories and DRAMs. Virtual memory provides a very high-level abstraction as just a linear sequence of bytes. It also provides a lot of other useful abstractions that make many different parts of the system much easier to manage. Okay, so we'll learn about virtual memory. We'll learn how it works. We'll learn about the potential performance impact that it has on your programs. And we'll also learn how to manage that large pool of memory that it makes available to you. And the lab that we do that, the lab where you'll do that is called Malloc Lab. And in the Malloc Lab, you'll write your own malloc and free functions. Okay, so you'll re-implement the functionality of the libc malloc and free. And this is maybe it's 2 pages of code, but I guarantee it'll be the most sophisticated, difficult 2 pages of code you've written. Not only because since it's managing the memory system, you can't use all of. I mean, C doesn't help you out a lot with abstractions for data structures. But when you're writing, at least it does give you ideas like structs, unions that you can use to structure your memory. When you're writing a malloc package, you can't use any of those. You have to rely exclusively on pointers and casting because the malloc package is working at such a low level. And so it's a very, very difficult piece of code for that reason. But also the design space for malloc is enormous. You have many options. They all have implications that trade off performance and memory efficiency. And finally, in the last part of the course, we deal with I/O, input-output. So far in the course, we just talked about sort of running programs on machines. In the last part of the course, we'll talk about input and output, sending data into and out of the machine. So we'll look at basic concepts of Linux I/O. And since I think the most interesting form of I/O is networking, which allows you to talk to machines anywhere in the world using the internet, we'll learn how to do network programming. You'll learn how to write programs that use the sockets interface, which is the basic interface for the internet, to talk to machines, potentially any machine in the world. And that's really exciting. I mean, I can still remember when developing this course, I had 2 windows open on my machine. I was SSH'd into 2 different machines, and I wrote a program to send a message like hello world from one machine to the other. And when that hello world appeared on the second window, it was like so exciting. I mean, if you're a nerd, it's really exciting. But just the thought that could have been any machine, right? That could have been any machine. It's just okay. All of our engines are using a system called Autolab, which was developed here, and you can access it if you were on the roster as of this morning. If you go to the Autolab link, then you'll see this course listed on your page. If you're not enrolled, you won't have an Autolab account. Now, you should contact one of these either semester.
Okay. So we did lecture 01. I'm actually going to rename these things to be like LT01 maybe? LE01? Yeah, because chapter 01 would be the actual book contents. So I'm going to say LE01. So what are we doing here? We're going to say, hey, finish lecture 01. I'm wondering how far I should go with the lectures before I start jumping into the reading. So tomorrow morning I have gym at 6 a.m. Let me check my calendar. Let's see here. Can I zoom out? There we go. Yeah, I just have the gym tomorrow. So I have gym at 6 a.m. though. And that means I'm going to wake up at 5 in the morning. So that means I need 3 hours subtracted from 12. I need to be asleep by 9. 7 already, so I need to start winding down to get to bed. So I can't jump into the reading immediately here. But one of the things I do want to answer here is how far does the reading go here? Because I think a tour of computer systems, like, that's like, I could just read that now. Because all of the next stuff about, sorry, I'm on the wrong screen here. Lectures 2 and 3, bits, bytes, integers, floating point. Like all of that is representing and manipulating information. And some of this is probably going to be chapter 3. So I think this is chapter 2. So that means I can get into chapter 1 right now. Like I don't need to, I think continuing into the lectures would be inappropriate at this point. I think I need to finish chapter 1, start on chapter 2, and then maybe start watching some of the lectures. All right. Let's see. That's the videos. This Labs app, or Labs link, sorry. Can I glow read me? Let's see. Can I click on this link? Hey, look at that. So he's got the bomb here. This is so cool. I'm gonna star it. And I'm gonna clone it. Let's go ahead and we'll do a submodule. We'll do it over HTTP because I don't imagine needing to contribute to this. And we'll do get submodule add repository path. Get submodule add repository, and the path will be labs. And if I do get status here, I just have this get modules, which links that up. If I cat out labs is a directory, but it says new file. That is interesting that they do that way. Okay. Something I would want to be able to probe here is like in my get staging index, I have a object. How do I dump this object out with get the raw object out? So we say get ls files -s. So we got labs here. So now we got the hash. So now we say get cat file -p, this guy. says it's not a valid object name. What about this? Get cat file dash p. So these aren't objects, are they? Yeah, they are. Is this the SHA of 877? Is that the SHA of, yep, 8716? So it's clear that the SHA is being recorded as the file, but it's like, type. Get cat file t. Get cat file p. Riddle me this, Batman. So this is cool that they have this self-study stuff. So the bomb is something that would be cool to it is pretty cool. The shell, I'm kind of curious about that one too. Oh wow, they got traces. What is this? Oh, these are like test cases? Damn. How much do they already have implemented here? I mean, they already have like 500 lines implemented. So they're trying to be nice to the students, I think, and allow them to focus on less of the guts of the shell, like signal handlers, and it even does job control. Wow, fuck, man. I'm gonna do a fork here. So I'm gonna go and say fork this. Maybe I should fix these headers a little bit. Yeah, I got the syntax right. Course book labs lecture. So in here, I'm gonna say course. Oh, and this needs to go like this. Book. Oops. Labs. Course book labs lectures. There we go. That looks a little bit better. Let's go to our K and R. And I'll log off here in a couple minutes. Let's fix up the README here. There we go. Much better, much better. Any other repos I need to fix up? Customize my pins, learn log, KNRC, ePOL file server, CS app, Linux programming interface, say pins. I think learn log should be top, then CS app. Yeah. Did I do the same thing for this? Yeah. I need to get dinner too. Alrighty. Think that's it for me today. Can kill that. We'll come back to this at some point. Oh, I did want to see like Adrian Cockcroft. That was a Netflix guy, right?
And the things that are important to us.
Oh yeah, there's another talk that I wanted to watch on stream at some point. Let's jump over to learn log. I think I already have it in here, but I just want to make sure. Oops. Let's just do RX. Yeah, this one here. Data one. Sorry, I have that. So I'm just gonna close that out. We'll come back to this, and I'll complete my notes some other time. Let's just record the timestamp 44:36. We'll just say, hey, 44:36. Where we left off, just in case it gets crashed or whatever. Alright. And then what was this thing for? It's just something that came up. Okay. Cool. Alright, I am going to be on tomorrow all day, assuming I don't get sick overnight. But yeah, I think tomorrow I'm going to start doing the reading on chapter 1, because chapter 1, it seems like chapter 1 and some of chapter 2 is very much up for grabs before I go into any of the other lectures. And I did want to look at chapter 1 to see if they have exercises in here. Let's see. It's very much an overview. Oh, was that an exercise? Yeah. Practice problem 1-1. So they got practice problems going along with this book. And then at the end, they have the solutions. Okay, that seems to be how they're doing it. Practice problems throughout the text. What is this? Okay, so they got lots of stuff in here. And just the chapter 2 is like you have to get to 180. Wow. And they have solutions for all the practice problems. Okay, do they have are these all solutions? Or these exercises? Let's see. Homework problems. God damn. So they'll have at the end of the chapter, they'll have more problems. So 254 is the last practice problem in the text of the chapter. And it starts 255, goes all the way to, and these don't have solutions in the book. These are, you get your own solutions. So 55 all the way up to 97. So it's basically about like 42, 43, 42. 42 problems at the end of this chapter. This is a book, my friend. This is quite the book. They're not messing around here. And the professor was saying, read each chapter 3 times. I think I'm in for some fun here. Okay, so tomorrow will be, the time I get on stream will be on reading the first introductory chapter, doing the first couple problems that they have. But it looks like getting into the later chapters 2 and above is where the rubber really hits the road. So, yeah, I'm excited. Cool. I'll go ahead and get off here then.